this is the atomic structure reverse the classroom video. Right, so this is kind of like the pattern through it. What we have to do is you have to go through the structure of the atom, isotopes, models of the atom, radioactive decay, equations, half-life, contamination and radiation, talk about background radiation, uses of radiation, right, and then fission and fusion is then the triple content section. Right, so firstly an atom. Atom has the same number of protons and electrons, so it's the same number of positives and the same number of negatives. An ion has an unequal number of electrons to protons, so sodium has got a plus charge, which is an ion, which means it's lost an electron. Okay, so metals tend to be positive and non-metals tend to be negative. The mass number is the number of protons and neutrons. Okay, so if I've got sodium 23 and 11, the mass number is this number at the top, which is the number of protons and the neutrons, and the atomic number, which is this number at the bottom there, is the number of protons only. Neutrons, protons, and electrons. Just be very careful, right? Because what I would tend to do is I'd normally do pen, protons, electrons, neutrons. Okay, so just be careful about the order that they put them in. So a neutron has no charge, it's got a size of 1, and it's found in the nucleus. A proton has a positive charge, size of 1, which basically means they are the same size, and it's also found in the nucleus. An electron has a negative charge, it's tiny, small, negligible, and what it does, it orbits the nucleus in shells. Now, history of the atom. This seems to come up loads and loads and loads of different times. Okay, so first guy, Democritus, he came up with the idea that atoms cannot be cut and came up with the idea of atomos. So what you can do is you can see where the word atomos came from. John Dalton, he then came up with the principle that they were solid spheres, and he also came up with the idea that there were compounds. And he kind of worked that out from water, which is H2O. So he worked out there was 2 spheres of H and 1 sphere of O. J.J. Thomson is then the plum pudding guy. Okay, and what that basically meant was the plum pudding is it had negatively charged fruit in it, and the rest of it around the outside of there was positive. Okay, a bit like a Christmas cake, a bit like a chocolate chip cookie, where the chocolate bits are then the negatively charged parts in it. Now Rutherford is then the main kind of guy, all right? And what he did is then he used alpha particles in something called the gold leaf scattering experiment. And he made 3 observations. The alpha particles passed straight through. That told him that it was mostly empty space. Alpha particles changed direction, got deflected. That meant that the positive alpha particles are deflected by a positive nucleus. So what he did is he came up with the idea that there must be something positive there for the positive alpha particles to kind of be deflected. A bit like a north and a north on a magnet, getting deflected, repelled away from each other. And he also noticed that some of the alpha particles bounced back. He concluded from that that the central nucleus is solid. Bohr, electrons are in circular orbits, shells. And then Chadwick, let's put an A there instead of Chadwick. He then came up with a principle that neutrons, because he noticed that the atom was lighter than it should be. Now this is then a little bit more on Rutherford's gold leaf experiment. So what he then had was, he had an alpha particle, so it's alpha and it's got a 2+, because what an alpha particle is, it's a helium nucleus. He shone his alpha particle at a piece of gold. Most of them went straight through. So his conclusion from that was empty space. Okay, and we can see this diagram on the right as well, where A, most of the particles went straight through, which meant there was empty space. B, okay, is then where some of them were deflected. So you got your alpha particle coming in, and some of them change direction. They didn't bounce straight back, they just changed direction. So the principle for that is your particle's coming in here, it goes near the positive nucleus and it changes direction. Okay, so that meant there was a positive center. And then C is then where particles go in and they bounce straight back. That is C, which is here, where the particles go in, they hit something and they come straight back. That meant there was a solid center. Now, isotopes. What I've got here is I've got 3 versions of oxygen. And what you could do is you could do pen for each one. So the number of protons on this oxygen is 8. Number of electrons is 8 because it's the same. And number of neutrons is 16. Take away 8, which is also 8. I can then do the pen of this one, the next one over. Protons is 8, electrons is 8, and neutrons 17 take away 8 is 9. Then I could do the pen of this one. Protons is 8, electrons is 8, and neutrons is 10. So these are all isotopes. So what you can do is you can see that an isotope is the same element, because that's the number of protons, but they have a different number of neutrons. Now, on to the 3 different types of radiation. We've got alpha, we've got beta, and we've got gamma. Now, what exactly is alpha? It's 2 protons and 2 neutrons. Okay, and often what we'll do is we'll call it a helium nucleus. Okay, so if you think about it, helium nucleus means it's just the middle bit, there are no electrons around the outside. And because it's got 2 protons, it's got a positive 2 charge, it can travel a few centimeters in air. It gets stopped by paper, and we can see that on the diagram at the bottom. Ionization is kind of like a bit like how much damage it can cause, right? How much damage it can cause to DNA is high. Beta is an electron. Because it's just an electron on its own, it's got a -1 charge. It says here few tens of centimeters, so it might maybe travel a meter. Stopped by a few millimeters of aluminium. Okay, we can see this in the diagram at the bottom here. And its ionization power is medium. Gamma, the final one, is a wave of energy. It has no charge. Range in air is infinite. It can just keep on going. It's reduced by a few millimeters of lead. Sometimes they'll say it's stopped by thick lead or thick concrete. And its ionization power is low. Now, what exactly are they? Okay, so an alpha particle is the helium nucleus that I mentioned before. So it's a positive, and it's a neutral and a neutral. This is then probably one of the most important things are its numbers. 4 at the top, 2 at the bottom. So that tells me it's got 2 protons. And at the top there tells me it's got 2 protons plus 2 neutrons. An electron, this is then the symbol you need to know for that. Right, so an electron has got a -1 at the top, a bottom rather, and a 0 at the top. And a gamma is literally just kind of like, it's a funny shaped Y really. All right, I kind of do it like, it's a bit like the breast cancer symbol, all right, a Y. And that is then an electromagnetic wave. Now this is then why it's important. This is then an alpha equation, a beta equation, and a gamma equation. Now what you've got to do here is you've got to notice the numbers. What they'll do is in your exam they'll leave some of these numbers on here blank, and you've got to then work them out. But you'll notice that 234 added to 4, so 234 added to 4 equals 238. So the numbers on the top must all add up together. And exactly the same, 92 equals 90 plus 2. So alpha is quite straightforward. Beta is then the one that catches people out. So on the left-hand side, we've got 14 and 6. So the numbers at the top make sense because 14 add 0 is obviously 14. But you've got 6 on the left, and then you've got 7 here, and you've got -1. So what you've got to do is you just got to remember that 7 take away 1 obviously is 6. But quite often what people will do is they will call the n at the bottom there 5, right, because you've obviously got a -1 there. So just remember the two numbers at the bottom must kind of equal each other. And gamma, the things just stay the same. Now this is then the piece of equipment that actually measures radiation, and it's called a Geiger-Müller tube, after the people that invented it. And what happens is the radiation goes into the Geiger-Müller tube, right, and then it is then detected. And it's what you do is you hear that kind of clicking noise, click, 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 right, is kind of the amount of radiation that's present. Now, around us all the time, we've got background radiation. Background radiation is radiation that is found in small quantities around us and originates from natural sources such as rocks and cosmic rays, so they're natural places, as well as man-made resource sources such as nuclear weapons testing and accidents. Okay, so background radiation is all around us, rocks, cosmic rays. Scotland, the Isle of Skye, has got loads of granite, which produces a lot of background radiation. Cosmic rays are from the sun. They are there all the time. We've then made things like nuclear weapons testing and potential nuclear accidents. Now, radioactive decay. So what you'll have is you'll have a particle. And what it'll do at some point, if it's a radioactive substance, it'll just decay, which means break down. Right, so what it'll do, it'll have an unstable nucleus. So in the middle there is an unstable nucleus. At some point, it will randomly, spontaneously emit the radiation that we've talked about, and that process is called radioactive decay. But the fact that it is random is the most important thing, in the fact that we don't know when the radioactive decay is going to happen. Two words that are kind of along those lines is we've got contamination and we've got irradiation. So contamination is the unwanted presence of radioactive atoms. So they could be in us, on us, in our food. Okay, so if I got a radioactive substance and I put it onto somebody's skin, that is then contamination. I gave them a tablet with radioactive stuff in it, that is contamination. Irradiation is when it is exposed. So this time my piece of radioactivity could be sat on the desk and the radiation is coming out of it, and that is then when somebody is exposed to it. Half-life. Okay, so half-life is the time taken to lose half of its initial radioactivity. So on this diagram, or this graph at the right hand side here, what it does is it starts off at 200. What you then got to do is you've got to think that half of its original, so when it starts off at 200, half of that is then 100, which will be here. So to calculate the half-life, what you do is you go right across from there, obviously using a ruler, and then you go down to there. So the half-life is then a time. So here it's about 1¼ hours, even though it'd probably be more accurate if I'd done it with a ruler. Then you'll have a second half-life, which is then from 50, because that's half of 100. You go across, and that's 2½ hours. So the half-life isn't 2½ hours, it's always the distance from one half-life end to another. So that would then be 1.25 hours, okay, or 1 hour 15 minutes. Now these are then the questions. You need to write these questions in your exercise book, right, and then answer them in full sentences. Write the symbols and numbers for alpha, beta, and gamma. So you're going to go alpha, beta, and gamma. And what I want you to do is write, well, I've just done the symbols for you. I want you to write the numbers next to them. Compare contamination and irradiation. What is an isotope? What were Rutherford's 3 conclusions? And what is a half-life?